Okay, thank you. So as mentioned, I'm going to be talking about how we use blue R's to connect microscale processes. So processes that involve the formation of different hydrometeors, so like graupel pictured on the left, and then hail, and then rain, and connecting these to mesoscale and thunderstorm phenomena such as downdrafts pictured here at the bottom, ultimately to try and improve cold pool parameterizations within larger scale models. So as I kind of just mentioned, we're connecting really small scale precipitation processes to larger scale thunderstorm phenomena. And so kind of our big scientific question that we're answering is what kinds of precipitation are the most important for forming, sustaining, and determining cold pool properties. And so why we kind of really care about this, so cold pools along their leading edge is kind of this outflow boundary, and along this boundary you can get new storm development. But within larger scale models that kind of require parameterizations, there's a lack of representation of convective components. So cold pools are not represented well. And the convective components, such as cold pools, are kind of driven by these small scale processes. And so because they're not well represented, they fail to predict long episodes of convective activity, which can have an impact in like rainfall in climate simulations and things like that. So in order to do this, we need a really detailed understanding of the physical drivers and the physical processes that form and sustain these cold pools. And this is going to require multiple realizations of really high resolution simulations with high frequency output, and that's going to give us really large data files. And so we need blue waters to be able to answer these questions. And so this is just a very simple diagram of a typical thunderstorm for those of you who maybe are more in the climate area and not the weather. So a very basic thunderstorm, you have an updraft, which is represented here by the red arrow, which is there kind of going into the storm. And then you're going to have a downdraft here, kind of pictured in the blue arrow. And downdrafts are kind of pockets of cold air, and they're cooled through latent cooling, which we'll kind of go into later. And then this pool of cold air is going to go down and hit the surface, and because there's nowhere else for it to go down, it's just going to kind of spread outward. And that's essentially just a cold pool. And so just as a spatial scale, so this is like a XY diagram. We have simulated reflectivity on the left with the cold pool kind of contoured in this black outline. So you can see this is kind of like a cluster of thunderstorms, and you've got this cold pool here. And these can span upwards to hundreds of kilometers, so they can grow kind of spatially larger than this. And they can also be quite cold, so theta perturbation at the surface is what we use to determine a cold pool. And so you can get these pockets of cold air that are like minus 10 Kelvin colder than the surrounding environment. And so going into precipitation processes, so as I described earlier, improving the parameterizations of cold pools is going to require a detailed understanding of what drives the cold pools. And so here's our very complicated flowchart about physical processes that occur in precipitation formation. And so what we're really trying to look at is we want to change the precipitating hydrometeor properties, which is down here, so graupel, hail, and rain. And so we're looking to change these in order to see what effect that has on cold pools. You can't really, within the models, just change like the amount or the size of these hydrometers directly. So what we do instead is we create variability in the initial fields. So that's going to be small ice crystals and small raindrops. And that's going to kind of have like a trickle-down effect. So in that way, we're able to change the hydrometeor properties. And this also has the added benefit of it's going to change the microphysics of the storm while keeping the dynamics relatively unchanged. So we're able to do kind of a more direct comparison between storms without worrying too much that there's different dynamics that are also going to influence this. And so to summarize once again, we're changing the initial precipitation processes. And these are governed by particles that are smaller than like the tip of a ballpoint pen to kind of look at how hydrometeors, which can range from like quarter size or nickel size for like rain, all the way up to tennis ball or larger for hail, and how that will ultimately influence cold pools, which can stretch hundreds of kilometers. So we're looking at a really broad range of phenomena across a lot of different scales here. And so again, this is going to require multiple realizations of high-resolution simulations with large domains and large output frequency to be able to quantify this. And again, this is kind of why we need blue waters. And so we use the CM1 model. It is Cloud Model 1. It was developed and is maintained by Dr. George Barnett and Carr. It's a 3D cloud model, and it was designed to be able to scale to however many processors that you need, so it can go tens to thousands. It's written in Fortran, and it's very user-friendly. There's quite a large range of user-specified like orders of integration, advection orders, and so on. And so one of the main things that we are using this for is because we also use the NSSL double moment microphysics scheme. And so double moment schemes will predict each hydrometeor mass and number concentration at each grid point, which is important for precipitation development. But the downside of this is it does increase the number of calculations and memory required. As I mentioned, we're looking at quite a large range of scales here. So our domains have to be large enough to encompass the cold pool. So they're about 250 kilometers in each horizontal direction, and then 20 kilometers deep. And our grid spacing is 250 meters with a time step of every 1 second. And so this means that we have about 80 million grid boxes in our domain for one of our realizations. And we have 12 simulations that we ended up with. And it costs about 800 node hours per run. And so this is pretty good because this is the most number of simulations that has been used to kind of address this topic. Like I said, we're using 12. Other studies have used around 5 or so. So we're getting some really good data from that. And this is also the highest resolution that's been used so far to kind of address this problem. So in looking at what forms cold pools, so what kind of kicks off the cold pool, we don't see a very consistent picture of what is happening within those downdrafts. We see some variability in the dominant hydrometeor that's occurring. So we have just percent of total latent cooling that's occurring in downdraft that forms the cold pool on the y-axis. And then all of our different model runs are kind of at the bottom. But the main thing from here is that in some of these runs, rain evaporation is most prominent, which is the green bar. In other runs, it's graupel melting, which is the red bar, and in others, it is graupel sublimation. So within the downdrafts that form cold pools, there's still a lot of ambiguity as to what processes are really the most dominant in there. And we also have discovered that there's kind of a range of downdraft strengths that form the cold pool. The kind of theoretical model that I think most people have is that the strongest downdrafts have the strongest or the most latent cooling, and those are the ones that form the cold pool. But we see from this that that's not necessarily the case. Even with the weakest downdrafts at 5 meters per second that form the cold pool, there's quite a range of latent cooling that's occurring within those. But the main takeaway from our cold pool formation that we've seen is that the speed of rain formation, so how quickly rain forms, it's also known as the warm rain process, does appear to be the most important for determining the cold pool onset. So when you have rain that forms more quickly, which is kind of this dark green bar here, the cold pool will begin quicker, and as it takes longer for kind of the rain process to begin and rain to form, you're going to really delay when your cold pool will form. Okay, and so if we now move on to cold pool sustenance, what is kind of keeping these cold pools going? How are they being fueled to keep going? So on the left, we have a plot of video, maybe, of theta perturbation. And so the darker blues are kind of colder areas within this cold pool. And this is, you can see the reference scale, so we're in like a 3D plane here. But you can kind of see that there, even though there's kind of a characteristic movement of the cold pool as a whole, as it's kind of moving kind of downward, there's still kind of these like bubbles that are in transient areas that are kind of there for a few minutes, and this is plotted every 30 seconds, and then kind of disappear. So they're very transient features still, not just kind of this big block of movement. That's kind of the simplified area. So then if we kind of look at the downdrafts that are plotted with it, so this is the same plot on the right, but now we have the minus 10 meter per second downdrafts contoured in the orange. We can also see that the downdrafts feeding into this cold pool are also very transient. So they're not always there. There's lots of them. They're kind of all over the place. And so this also makes it kind of difficult for us to try and figure out, well, how are we going to quantify the latent cooling within the downdrafts because they are so transient. So what we did is we created this kind of offline routine to calculate latent cooling in the downdraft. So what it does is the code is kind of going to search for the cold pool at the surface, which you can kind of see here. And then at each output time, which we're doing every 30 seconds, it's going to look for a downdraft that is kind of touching and feeding the cold pool. And if there's a downdraft there, it kind of checks it, and if not, it doesn't and moves on. And then it's going to go up a model grid level and also look at the adjacent points. And that's to account for any kind of downdraft funneling. And it's going to keep kind of doing this until we don't have any more downdrafts. So this is a bit timely and takes quite a lot of computational time to be able to run this for every model time step and for over 12 simulations. And that's also why we need blue orders for it. And then so if you look at kind of this nice kind of panel plot, you can see this is an XZ cross-section. The units are in grid points, and the solid black line is kind of the melting level. So we have simulated reflectivity on the top left, and then you could see the vertical velocity with blues being downdrafts, red being updrafts. And then with our latent cooling terms, the contoured lines are the downdrafts, and then you can kind of see in shading where kind of all of our latent cooling is occurring within these storms. So that's kind of the nice picture of kind of what our routine is doing to calculate latent cooling. And so now what we see with latent cooling in sustaining the cold pools, we see that graupel is the dominant hydrometeor for all of these. So within the panel plot, the bottom is in minutes, so 0, we're doing minute 0 is the time that the cold pool starts in each simulation, up to 50 minutes afterwards. And then we have latent cooling in joules, and that's 10 to the 16th. So even when we change all of the initial microphysics characteristics for these 12 different runs, graupel sublimation is still the most dominant term for all of them. And it's pretty similar percentage-wise. So graupel sublimation is about 50% across all the runs of the total latent cooling. Rain evaporation is about 30%. Graupel melting is 15%. And then hail has very minimal contributions. It's about 5% of the total latent cooling. But what we did see also was, even though graupel is the most prominent hydrometeor within the downdrafts, rain evaporation has the strongest influence on the cold pool properties we looked at, which is expansion rate, depth, and strength. And so here you can see kind of each dot represents a simulation. So we have the total latent cooling, rain evaporation, and then graupel melting and sublimation, and hail melting and sublimation. So you can see and this is expansion rate for this plot, you can see that the rain evaporation term is pretty well correlated between the expansion rate and the amount of cooling that's occurring. And so we are theorizing that this is because rain evaporation is occurring within the cold pool, so it's occurring at the lowest levels. If we kind of look at this just visually, you can see that. So rain evaporation is in green here, and graupel sublimation is in this purple-pink color. So even though we have quite a large area of the stronger graupel sublimations, it's occurring higher up as opposed to the rain evaporation, which is kind of occurring at a lower level. And we also check this quantitatively. So if we eliminate our latent cooling calculations to, say, like 2 kilometers, we can see that rain evaporation, which is kind of the green dotted line, is the most dominant term. There's pretty much no influence from graupel or hail. And as we kind of go up to 4 kilometers, there's more graupel influence. There's a changeover at about 5 kilometers where graupel is now the dominant hydrometeor. And then that kind of continues all the way up. And so this has actually been really helpful because it's helped to reconcile differences that we've seen in past studies. So past studies have also seen that rain evaporation is the most important for cold pool properties, but they showed that rain was the most dominant hydrometeor. But they capped their latent cooling calculations at 4 kilometers. So if you do that here, you do see that rain evaporation is the most dominant. But if you look through the entire kind of depth of the atmosphere, graupel is the major contributor. So this has really also helped clarify kind of the picture of what's really going on. And so just to summarize the research that we've done, so we use BlueWires, again, to connect the precipitation processes to thunderstorm phenomena by changing the initial precipitation processes. Again, and those are governed by very, very small particles, and then that'll ultimately influence how rain and graupel and hail form, which will ultimately influence cold pools. And so we saw that the rain processes, so how quickly rain forms, also determines how quickly a cold pool will form. We saw that graupel is the dominant hydrometeor that sustains the cold pool, but rain evaporation has the strongest influence on the cold pool. And so from this work, we were kind of able to suggest some implications for larger scale weather and climate models and how this research can be adapted to go back to our big picture question of improving parameterizations. So we do kind of note that you do need to at least somehow can link the microphysics to a cold pool parameterization in order for this to be accurately represented. Cold pool onset could be parameterized using local CCN values and cloud-based temperatures. That could kind of proxy how quickly rain forms. And then large amounts of near-surface rainfall could be used to help parameterize the cold pool properties, since we saw that rain evaporation really has strong ties to the cold pool properties. But cold pool sustainment and how the longevity of and length of cold pools is governed by graupel, but more work is needed here because graupel is kind of related to the amount of ice nuclei, which is not well quantified. And another kind of hurdle with that is a lot of microphysics schemes will only allow for the prediction of graupel or hail, and that's just for computational reasons. So there needs to be a bit of work on how to best implement that. And then so computing is not without its challenges, even at the petascale, but over the years we've kind of figured out better ways to kind of solve these. So we have, one of the problems we've had is NCL routines kind of running out of memory and kind of slow speeds with the 3D visualization and NCL codes, but we have kind of trimmed down our data files using a routine to remove a lot of the empty space and some of the variables that you may not need around them. And so this also helps with the analysis and longer term storage because it really cuts down on the file size. And then searching large domains for continuous services meeting certain criteria, which I kind of showed with that algorithm we used for searching for downdrafts and cold pools. So we have been using kind of these cumbersome Fortran and NCL routines, but someone else in our research group is working with BlueWires to develop a MATLAB routine that is better for both memory and computational speed.